Hello, and thank you for joining me today. My name is Trevor Ballard, and I'm a PhD candidate at the Advanced Steel Processing and Products Research Center at the Colorado School of Mines. The title of my presentation today is Double Twist Torsion Testing to Assess Partial Recrystallization in Microalloyed Steels. And before beginning, I would also like to thank my fellow co-authors on this work for their contributions, Dr. John Spear, Dr. Kip Finley, and Dr. Emmanuel Demore. For my presentation today, we will begin with some background information on the non-recrystallization temperature, or TNR. And then we'll look at how TNR relates to the controlled rolling schedules that are used to process microalloyed steels. And then we'll go through some experimental techniques used to determine TNR. After that, we'll go through the experimental procedure for the current study and look at double twist torsion testing to predict changes in recrystallization through fractional softening calculations. We'll go through results and conclusions, including a prediction of the temperature region of partial recrystallization using the double twist torsion test, and then look at the relationship between TNR and this region of partial recrystallization. So to start, we'll look at the non-recrystallization temperature, or TNR. And TNR is commonly defined as the transition from complete to incomplete recrystallization between two stands in a rolling mill. While this is a common definition, there is not a standardized definition of TNR or testing method to determine it. And as such, there are discrepancies in the observed recrystallized fraction noted in the literature. So some authors have noted 90% recrystallization near TNR, and this is pretty consistent with the definition as the transition from complete to incomplete recrystallization. Other authors, however, have noted substantially less recrystallization near TNR, with a recrystallized fraction of only 50 to 65%. So in addition to this, a variety of parameters can affect TNR, including alloy content and deformation conditions such as strain, strain rate, and inner pass time. In practice, TNR is used to develop the controlled rolling schedules that are used to process microalloyed steels. Controlled rolling schedules enable the desired microstructure to be achieved during hot rolling itself rather than during post-rolling heat treatments. The reduced need for heat treatments after rolling substantially reduces the cost of microalloyed grades. However, development of effective controlled rolling schedules requires an understanding of the recrystallization behavior of the material, and this is typically put in the context of TNR. So roughing passes are conducted above TNR, where complete recrystallization occurs between passes. The material is then cooled below TNR, and ideally below the full range of temperatures where partial recrystallization occurs, into a regime where recrystallization is fully suppressed. Finishing passes then take place below TNR, and this is where we achieve our desired microstructural control. It's important to note that we generally avoid deformation in the region of partial recrystallization, as this has been shown to lead to a non-uniform grain size in the final product with reduced toughness. So therefore, it is advantageous to be able to predict the entire temperature range over which partial recrystallization occurs, and that is ultimately the focus of this presentation today. Before getting into that, though, we'll discuss some of the common techniques used to determine TNR. And we'll start with double hit compression testing. So the general procedure for this is to reheat the specimen to a temperature where microalloying additions are in solution, cool to a deformation temperature, and then compress the specimen with a given strain and strain rate. The specimen is then held for an inner pass time before being compressed again with the same parameters. And this results in a set of true stress, true strain curves, and there are some examples on the upper left here for varying inner pass times. And to determine TNR with double hit compression testing, double hit tests are conducted at a variety of temperatures using a new specimen for each temperature. The fractional softening is determined for each temperature, and TNR is defined as the temperature corresponding to 20% fractional softening. And there are several methods that can be used to determine fractional softening, and there are some examples on the right-hand side here, and these will be discussed later on. But some examples are the 0.05 true strain method, the mean flow stress method, and the offset method. And I highlight these specifically because, like I said, we'll use these later on in the present work, but literature has shown that there is a direct correlation between the fractional softening calculated with these methods and the recrystallized fraction. And so this represents a big advantage of double hit compression testing, that we can take the mechanical data generated during the test and directly relate it to the extent of recrystallization in the material through these fractional softening calculations. The downside of double hit compression testing, however, is that we are limited in how much strain we can impart to a single specimen without excessive barreling. And this is why we use a new specimen for every temperature. And so effects of multiple deformation passes on recrystallization behavior are not typically captured with double hit compression testing. So as an alternative, Multi-step hot torsion testing has also been used for determining TNR, and the general procedure for this type of test is to reheat the specimen to, again, dissolve microalloying additions, cool to the first deformation temperature, and twist the specimen with a given set of parameters. The specimen is then cooled to the next deformation temperature and twisted again with the same parameters, the same strain and strain rate. And this process of cooling and twisting is repeated for every temperature of interest in the rolling schedule being simulated. And this results in a series of torque twist curves for each deformation temperature that can then be converted into equivalent or effective stress strain curves. And so you can see an example of the series of equivalent stress strain curves for a single multi-step hot torsion test on the upper right-hand plot on this slide. To calculate TNR from the multi-step hot torsion test, we then determine the mean flow stress for each pass and plot this as a function of inverse deformation temperature. And you can see a plot of mean flow stress versus inverse deformation temperature on the bottom right-hand plot. And in this plot, we see two distinct linear regions, and region 1 on the left-hand side of the plot corresponds to high temperature deformation, where the increase in flow stress is due to a reduction in temperature alone. At lower temperatures, as we approach the right-hand side of the plot, we see that mean flow stress increases at a faster rate. And this, in the case of microalloyed steels, is attributed to the precipitation of microalloying additions as carbonitride particles that impede recrystallization, leading to the accumulation of strain between rolling passes. So if we define TNR as the transition from complete to incomplete recrystallization, we have TNR corresponding to this inflection point separating regions 1 and 2, as highlighted on the plot on the bottom right. So multi-step hot torsion testing has the advantage of applying multiple deformation steps to a single specimen. And so this is generally more representative of an industrial rolling mill, and effects of multiple deformation passes on recrystallization behavior can be captured. There is, however, no correlation to fractional softening and no direct relationship between the recrystallized fraction and the inflection point used to define TNR for the multi-step hot torsion test. So therefore, to fully characterize recrystallization behavior using multi-step hot torsion, direct microstructural observation is generally required. So finally, I would like to describe a newly developed double twist torsion testing technique for calculating TNR and assessing recrystallization behavior. So this was originally developed in ASPPRC by me and the fellow co-authors on this work using a 316 stainless steel. And the general process for this, there's a schematic on the right-hand side, is to reheat to dissolve any microalloying additions, in the case of a microalloyed steel, cool to the first deformation temperature, and apply a pair of torsional isothermal deformation passes separated by an inner pass time. So this is similar to a double hit compression test, and it allows us to calculate the fractional softening at a given temperature. And from these fractional softening calculations, changes in recrystallization behavior can be inferred. But because we're in torsion, we can cool the same specimen to the next deformation temperature and apply another pair of isothermal deformation passes. And we can repeat this double twist process any number of times on a single specimen to simulate rolling over a range of temperatures. So this is similar to a multi-step hot torsion test, and effects of accumulated strain can be studied with a double twist torsion test. And so this leads us to the research questions for the present work of, can we predict the temperature region of partial recrystallization using these fractional softening measurements? And then how does TNR, as determined with double hit compression testing or multi-step hot torsion, compare to this region of partial recrystallization? So the alloy used in the present study is shown here on the slide, and it is a niobium vanadium bearing microalloyed steel with a small titanium content. And this alloy was used in prior work in the Advanced Steel Processing Products Research Center by Karen Homscher. And her research focused on comparing TNR for double hit compression and multi-step hot torsion testing. And so the reason this alloy was selected for the present work is because we already had TNR values for both double hit compression and multi-step hot torsion. So from the work done by Karen Homscher, double hit compression testing resulted in a TNR of 1000 degrees C, and also from Karen Homscher's work, multi-step hot torsion testing resulted in a TNR of 968 degrees C on this alloy. And these were determined using a pass strain of 0.2 and a strain rate of 5 per second. So for the present study, the double twist torsion test was applied to this alloy in And we use deformation temperatures from 1200 to 800 degrees C and 50 degree decrements. We used a 5-second isothermal interpass time between deformation passes at each temperature, and then a cooling rate of 2.5 degrees per second in between deformation temperatures. And to keep the work consistent with what was done in Karen Holmscher's studies, we used a pass strain of 0.2 and a strain rate of 5 per second. Fractional softening was then determined for each temperature using the methods that I described previously, so the 0.05 true strain method, the mean flow stress method, and the 2% offset method. The temperature region of partial recrystallization was then defined as the range of temperatures between fractional softening values of 80% at the upper limit and 20% at the lower limit. So now we'll look at some of the data generated during double twist torsion testing on our Gleeble 3500. So at the right, we see the series of effective stress strain curves from the double twist torsion test, and we see there are 2 stress strain curves for each temperature, and multiple temperatures can be studied with a single specimen. And so this is to, again, account for the effect of multiple deformation passes on recrystallization behavior. Fractional softening was then determined for each temperature, and changes in recrystallization are inferred from these fractional softening values. So if we look a little bit closer at a couple of the double twist pairs, we can see how the shape of the second stress strain curve varies with respect to the first, based on the temperature and based on the extent of recrystallization during the interpass time between both hits. So we have here the pair of stress strain curves from the double twist torsion test at 1150C and 850C. And these are the same stress strain curve shown in this slide, just individually. So for high temperatures like 1150C, shown by the plot on the left, we see that the curves are nearly identical to each other. So the second stress strain curve is nearly identical to the first, and this indicates extensive softening and therefore extensive recrystallization during the 5-second interpass time between these 2 deformation passes. If we compare that to deformation at lower temperature, like 850 degrees C, shown by the plot on the right, we see that the second stress strain curve is a continuation or an extrapolation of the first. And this indicates minimal softening and therefore minimal recrystallization during the 5-second interpass time between these 2 deformation passes. So next we'll look at the fractional softening calculations from each of the 3 methods that I mentioned previously to predict the temperature region of partial recrystallization. So we'll start with the 0.05 true strain method. And here we have the equation used to calculate fractional softening according to the 0.05 true strain method. And we have several different stress terms. We have the sigma m, sigma 2, and sigma 1. So sigma 1 and sigma 2 are the stress values at a 0.05 true strain offset for the first and second deformation passes in the test. Sigma m represents the stress at a 0.05 true strain offset for a stress strain curve corresponding to the condition of 0% softening. So remember from before, at low temperatures where we have very little softening, very little recrystallization, the second stress strain curve is essentially an extrapolation of the first. So to determine this sigma m term, we extrapolate the first stress strain curve to create this hypothetical second stress strain curve, and then take the stress value corresponding to the strain at 0.05. So plotting fractional softening versus deformation temperature, we see the plot on the right, and this follows approximately sigmoidal behavior. And we have a temperature region of partial recrystallization bounded by 1032 degrees at the upper limit and 912 degrees at the lower limit. And if we recall our TNR values from double hit compression of 1000 degrees and multi-step hot torsion of 968 degrees, we see that TNR lies within this temperature region of partial recrystallization. So not necessarily at the transition from complete to incomplete recrystallization, which would be around 1032 degrees C from the 0.05 true strain method, but somewhere within the partial recrystallization regime. So now let's see how the mean flow stress method compares. So from the mean flow stress method, we have our equation here to calculate fractional softening. And this method is based on the areas under the 2 stress strain curves. So sigma 1 and sigma 2 in this case are the areas under the first and second deformation, or the first and second stress strain curves. Sigma m is again based on an extrapolation of the first stress strain curve to create a hypothetical stress strain curve corresponding to the condition of zero softening. And so sigma m then is the area under that hypothetical second stress strain curve corresponding to zero softening. And plotting fractional softening as a function of deformation temperature, we have a partial recrystallization temperature range bounded at the upper limit by 1037 degrees C and at the lower limit by 920 degrees C. And this is fairly similar to what we saw in the case of the 0.05 true strain method. So we see a good correspondence between these two methods to calculate fractional softening. And again, our TNR values of either 1000 degrees or 968 degrees are well within this partial recrystallization regime. And again, also not necessarily at the transition from complete to incomplete recrystallization. So finally, we'll look at the 2% offset method. And the 2% offset method is based on the yield strengths of the first and second deformation passes. So in this case, if we look at our equation for calculating fractional softening, our sigma 1 and sigma 2 are the yield strengths at a 2% offset of the first and second deformation, the first and second stress strain curve. Sigma m is again based on that extrapolation of the first stress strain curve and is taken as the yield strength of the second stress strain curve based on the extrapolation of the first. So plotting fractional softening versus deformation temperature, we have a predicted partial recrystallization temperature range bounded by 1040 degrees C at the upper limit and 874 degrees C at the lower limit. And so again, our TNR values of 1000 or 968 degrees C, depending on the method used to calculate TNR, is well within the partial recrystallization regime predicted by the double twist torsion test. So we've seen that each method for calculating fractional softening results in similar temperature limits over which partial recrystallization can be expected. And in addition to that, we've seen that TNR lies within this range for each method. So now we'll look at the effect of multiple deformation passes on recrystallization and fractional softening. And we'll do this by comparing the double hit compression test to the double twist torsion test at 1000 degrees C. So from the previous research that I mentioned by Karen Holmshire, it was found that double hit compression testing consistently resulted in a higher TNR than multi-step hot torsion testing. And this was attributed to the multiple deformation passes inherent to the multi-step hot torsion test, leading to increased grain boundary area, and having this increased grain boundary area essentially promote recrystallization and lead to a lower TNR than double hit compression testing, which only undergoes 2 deformation passes per temperature and per specimen. So if we look at fractional softening at 1000 degrees C for the double hit compression test and the double twist torsion test, we see that from double hit compression testing, based on the definition of TNR, at 1000 degrees C, we have a fractional softening of 20%. If we compare this to double twist torsion testing at 1000 degrees C, where we've had a total of 10 deformation passes, if we include those at 1000 degrees C, we have a substantially higher fractional softening of 67 to 68%. And so we see that increased softening, and we can infer then increased recrystallization, was calculated at the same temperature for the double twist torsion test in comparison to the double hit compression test. And this supports the hypothesis that multiple deformation passes ultimately promote recrystallization, and this appears then to be a valid explanation for why we consistently see double hit compression testing resulting in higher TNR values than multi-step hot torsion. So to wrap up, we have applied a newly developed double twist torsion test to a microalloyed steel and used it to predict the temperature regime of partial recrystallization using 3 different methods for calculating fractional softening. And this is based on the correspondence between fractional softening calculations and the recrystallized fraction noted in the literature. And all 3 methods that we used to calculate fractional softening resulted in fairly similar temperature limits of partial recrystallization. In addition, we can see the partial recrystallization can be expected over a fairly wide range of temperatures, over 100 degrees C range in each case, regardless of the method used to calculate fractional softening. And so how does the temperature range of partial recrystallization relate to TNR? Well, the calculated TNR from work by Karen Holmshire lies within the temperature regime of partial recrystallization predicted by the double twist torsion test on the same alloy. So it's not necessarily the precise transition from complete to incomplete recrystallization, but within the partial recrystallization regime. So use of TNR, which is a single temperature, may not fully characterize recrystallization behavior, and the double twist torsion test may allow controlled rolling schedules to be developed with greater precision as we can predict the full range of temperatures over which partial recrystallization can be expected. In addition to that, we see that the application of multiple deformation steps results in increased fractional softening for a given temperature, and therefore increased recrystallization. So with that, I would like to thank you all for your attention. I would like to thank the sponsors of the Advanced Steel Processing and Products Research Center, and I would be more than happy to answer any questions that you might have regarding this work. Thank you.